When covering hydrostatics in lecture earlier this week, I mentioned the idea that we could handle pressure prisms in a slightly different way if the gates themselves are rectangular. And I want to just cover that briefly today. So let's suppose that we have a rectangular section that is being affected by hydrostatic force. And what I've sketched here is the pressure prism that's acting on that gate. The effective force that's acting on the gate is our hydrostatic force, and it acts, as we've discussed, below the centroid of the gate itself. So here's our hydrostatic force, and we have some distance here. Let's say this entire width of our gate is capital L. Then the distance to which the effective force acts is greater than halfway down, so L is greater than L over 2, and the specifics of how much further below the midpoint it acts, let me just rewrite that. L is greater than the half of the width of the gate. It depends on how far below the surface we are, and that's where we apply our relationships for the center of pressure or the line of action and define the magnitude of the hydrostatic force. Now, I'm going to flip to a second slide here and kind of rework this problem in a slightly different way. So here we would take the approach where F hydrostatic, just to remind you, is the pressure at the centroid times area, and the location of the center of pressure is equal to the centroid plus the second moment divided by yc times A. Those two relationships together specify this hydrostatic force that we've sketched here, single force. Now, going to a new slide. Instead of a single force with a single moment arm, coming back to the second slide up. Okay, so what I've sketched here is that same rectangular gate of height L. This is the pressure acting on that gate. What I'm going to do now, though, is I'm going to divide the pressure prism into two parts. And I'm going to define one part to be this uniform pressure that's acting everywhere on the gate in the same way. So it has some pressure, let's call it P0, and the effective force of, let's call this F1, the effective force due to these blue arrows, F1 is just P0 times A, and it acts through the centroid. So to sketch that as a say a red arrow, acts through the centroid. So this is F1 through the centroid. I didn't draw that right in the center. I should have. Should have been down here. But so the reason it acts through the centroid is that this force is now uniform. There's no variation, so the average position of the force is at the centroid. Now that's not true for this triangular element. So now I'm going to define F2 to be the net effect of this triangular element. It will act below the center line because it increases with depth. And in fact, it acts at a particular location below the center line, F2. The magnitude of F2 is going to be the pressure at the effective pressure at the center of that triangle. So F2 is equal to, I'll call this little pressure here P2. P2 times the area of the gate. Now the line of action, it acts 2/3 of the way down. And that's because the second moment, or the centroid of this triangle, I should say, the centroid of this triangle is 2/3 of the way down. So the average position of the forces is 2/3 of the way down. So we could analyze the moments of this single hydrostatic force. Instead of, I'm going back to the first slide, we could think of it as two forces, one acting through the centroid, one acting 2/3 of the way down, each given by pressure times area, where pressure now consists of, in the case of F1, the uniform part of the pressure, and in the case of F2, the centroid of, or the average of the pressure in the triangular portion of the pressure prism. Okay. This may be a confusing way to construct this, It's not necessary to work with them in this way. I introduce it simply as an alternative to the single force analysis, keeping in mind that this is appropriate for rectangular or square gates where the width is constant with depth.